we're going to dive in and take a closer look at an application of the law of conservation of momentum by a closer examination of collisions. Specifically, we're going to look at 2.5 different kinds of collisions. One kind is called elastic, and that is the collision that involves the perfect bounce between the colliding objects. The second type of collision is the inelastic collision, which is a less than perfect bounce. And then there is the perfectly inelastic collision, which is like inelastic, but it has one very particular property that makes it quote-unquote perfect. But before we get there, we're going to start with elastic collisions. So you have undoubtedly bounced balls off the ground, off the concrete, whatever. And if you just drop one and release it, some balls bounce higher than others. If you were to drop the ball and it were just to keep bouncing to the same height over and over, world without end, amen, for the rest of eternity, then you know that what you have is the perfect bounce. It is perfectly elastic. And most bounces aren't like that. Most bounces have some loss, and some of them, maybe a blob of putty, would just kind of splat on the ground. So there are different categories. That's what I mean by elastic, in that it is the perfect bounce. It is the one that would keep on going forever and ever and ever. And it turns out that if the collision is elastic, and you'd be surprised, there are some collisions that can be very reasonably approximated as an elastic collision. If you see an elastic collision as a problem, then you know that kinetic energy is conserved. Now, it's a collision. I don't care what kind of collision it is, momentum is always conserved. But in an elastic collision, kinetic energy is also conserved as a way of recognizing that it is the perfect bounce. So at the bottom of this slide, you see two equations. One is the law of conservation of momentum, which always applies, period. The second one is how we can encapsulate the idea of conservation of kinetic energy in an equation. So 1/2 m1v1 initial squared plus 1/2 m2v2 initial squared equals 1/2 m1v1 final squared plus 1/2 m2v2 final squared. This is not normally conserved. It has to very specifically be in an elastic collision for us to say we have conservation of kinetic energy. It doesn't occur in any other kind of collision. When we get to inelastic, the idea of conservation of kinetic energy flies out the window. We have no truck with it. But for elastic collisions, these two equations can be algebraically manipulated. The algebra is annoying, so I'm not going to require you to know it, and I'm not even going to show the derivation because I don't think that all of the algebraic manipulation is really that educational. What you get at the end are expressions for the final velocities of the two different objects. You get an expression for V1 final and you get an expression for V2 final, and each of those expressions is in terms of the two initial velocities, V1 initial and V2 initial, as well as the masses of the different objects. If you look closely at those equations, you'll see that there's kind of some parallels between them. For instance, V1 final, you see M1 minus M2 over M1 plus M2 times V1 initial. And for V2 final, you see minus M1 minus M2 over M1 plus M2 times V2 initial. In the first equation, you see 2M2 over M1 plus M2 times V2 initial. And in the second equation, you see 2M1 over M1 plus M2 times V1 initial. Those parallels are there because it doesn't matter which object you call object 1 and which object you call object 2. It's just once you pick them, you got to stick with them. Let's take a look at those two equations and what would happen in two extreme situations involving masses. The two extremest situations possible are when they're equal and when they are extremely unequal. So if we look at the situation where M1 is equal to M2, what we find is a rather interesting result. If we go back to the equations, and if we assume that M1 is equal to M2, then for V1 final, this first expression disappears. If M1 is equal to M2, that numerator is 0, that's all gone. And the second expression, you would get 2M over 2M, which is 1. What you get is V1 final equals V2 initial. And in the second equation, for very similar reasons, you would get V2 final equals V1 initial. What that means is that in the collision, the two masses switch their velocities. No matter what those velocities are, if the two masses are equal and have an elastic collision, they swap their velocities. The other situation is when one mass is much larger than the other. So it doesn't matter which one we say. Let's say M1 is much larger than M2. And if we go back to the equations, if M1 is much larger than M2, then M1 minus M2 is basically equal to M1. M1 plus M2 is basically equal to M1. And what we get for this first term is V1 initial. The second term, M1, is huge compared to M2. So the denominator is huge compared to the numerator, which means that this is virtually 0. So what we're left with is V1 final is equal to V1 initial. For the other object, the one with the small mass, we get 2M1 over M1, which is about equal to 2. So 2 V1 initial. And then we get M1 minus M2 over M1 plus M2, which is basically equal to 1 because M1 minus M2 is still close to M1. M1 plus M2 is still close to M1. This cancels out and we have V2 initial there. If we apply this to the situation of a ball bouncing off the surface of the Earth, basically we can treat the Earth as stationary, and what we find is that the final velocity of the ball is exactly opposite to the initial velocity of the ball. So we get V2 final equals minus V2 initial, because even if we have a perfectly elastic collision between the ball and the Earth, the mass of the Earth is so huge that it basically doesn't move, and the ball exactly reverses its velocity. Take a look at this conceptual question. We have two parts, A and B. They look identical. They are made of the same material. We put A at rest on a frictionless air track, and we put B on it, and we push B towards A. And B collides with part A. And after the collision, both parts are moving to the right, although the velocity of part B has slowed down a little bit. Which of the following is a reasonable conclusion? Part A is actually hollow, or the two parts are identical, or part B is hollow, or we need more information. Think about it. Don't hesitate to ask questions at the start of class. Let's do an example where we apply those equations from a few slides ago. We have two masses undergoing an elastic collision. All we're told is that one mass is twice that of the other mass. The heavier mass has a speed of 15 meters per second. The lighter mass has a speed of 5 meters per second in the same direction. And the question is, what happens? Basically, what are the final velocities of these two objects? The masses weren't given, but we know their ratio. We can say that, if the first mass is twice the second mass, we can say M1 equals 2 M2. We're given that the heavier mass has a speed of 15 meters per second, and the lighter mass is moving in the same direction at 5 meters per second. And since I'm not told plus or minus, left, right, up, down, whatever, I'm just going to make both of those velocities positive. They're moving in the same direction. They're both positive. Why not? Then I plug into my equations. Make sure that you have assigned each velocity correctly to each object. So the heavy mass has a speed of 15 meters per second. If m1 is the heavy mass, then v1 initial is 15 meters per second. And that leaves v2 initial as 5 meters per second. And then you plug in. What should you expect? The heavier mass is basically rear-ending the lighter mass. I would expect the heavier mass to slow down a little bit, and I would expect the lighter mass to pick up a noticeable amount of speed. So I would expect the heavier mass to have a final speed less than 15 meters per second, and I would expect the lighter mass to have a final speed of greater than 5 meters per second. Well, what do I get? After plugging in, I get that the heavier mass has slowed down to 8.33 meters per second, and the lighter mass has sped up to 18.3 meters per second. You should be able to duplicate these calculations on your own. So that's it for the elastic collisions. The inelastic collisions, as I said, if it's not elastic, it's going to be an inelastic collision, which means some kinetic energy will be lost. It might be conceivable for all of that kinetic energy to be lost, but at least some will be lost. And if you're just told it's an inelastic collision, you have only one equation, conservation of momentum. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. That's it if you're told it's inelastic. But I mentioned the perfectly inelastic collision, which is a type of inelastic collision, but it has one particular property. In the collision, the two objects stick together. After the collision, they're moving as one object. If after the collision they are moving as one object, we can say V1 final equals V2 final, and we might as well just call that V final. And our expression for conservation of momentum simplifies a little bit. I have one less variable to worry about, and you can see the expression at the bottom of the page for the perfectly inelastic collision where the two objects stick together. M1 V1 initial plus M2 V2 initial equals M1 plus M2 times V final. Another conceptual question. A cart is moving at a speed V. It collides with an identical stationary cart on an air track, so we don't need to worry about friction. The two stick together after the collision. What is their velocity after they collide? So the first has a speed V. The second one, otherwise identical, has a speed of 0. After the collision, what is their speed? Is it V? Is it half V? Is it 0? Or is it negative 1/2 V? Again, don't hesitate to ask a question in class. Let's do an example of kind of a perfectly inelastic collision. But this is a perfectly inelastic collision running backwards. We start off with one solid object moving with some speed, and it breaks apart into two different objects. So it is a perfectly inelastic collision in reverse. We can still apply the same ideas. In this case, it's a 25-kilogram rocket moving at a speed of 250 meters per second, and it breaks up into two pieces. One of the pieces has a mass of 15 kilograms, which means the other one has to have a mass of 10 kilograms. Remember, it started off with a mass of 25 kilograms. The problem goes on to say the 10-kilogram mass continues on in the same direction at a speed of 275 meters per second. what is the velocity of the other mass? In other words, how fast is that 15 kilogram mass moving? So it is like a perfectly inelastic collision. It's just that the initial velocities are the same, and it's the final velocities that are different. So we'll say V1 initial equals V2 initial equals V initial, and therefore M1 plus M2 times V initial equals M1 V1 final plus M2 V2 final. M1 is 25. The sum of the masses is 25. M1 plus M2 is 25, and V initial is 250. On the other side of the equation, M1 is 10, and it has a speed of 275. The second one I'm saying is 15 kilograms, and it has this unknown speed of V2 final. Now, again, we should have a preconception of what to expect. So the overall system is moving at 250 meters per second, but all of a sudden a portion of that system starts to move faster. To maintain conservation of momentum of the system, the other part must start moving more slowly than 250 meters per second, and that's what we get, 233 meters per second. So this should agree with what you should be visualizing. Now, two-dimensional collisions happen. We can't keep everything happening along a one-dimensional line. Let's look at a two-dimensional plane. And what happens is we look at conservation of momentum, but we have to look at the x components of momentum for the different objects, and we have to look at the y components of the momentum of the different objects, and we treat the x stuff separately from the y stuff. So if you have two dimensions and you're looking at conservation of momentum, you really have two equations. M1 V1 initial x plus M2 V2 initial x equals M1 V1 final x plus M2 V2 final x. And at the risk of exhausting my vocal cords, M1 of V1 initial y plus M2 V2 initial y equals M1 V1 final y plus M2 V2 final y. So a two-dimensional problem is basically like two one-dimensional problems. The only hassle might be having to break your information down into x and y components separately. Here's an example. We have a collision between two particles. One of them is a 16 kilogram mass moving at a velocity of 4.20 meters per second, 25 degrees west of north. The other one is 11.5 kilograms. It has a velocity of 9.50 meters per second in a direction that is 12 degrees west of south. These two are allowed to collide. The question is, what are the magnitude and direction of the final velocity if this is a perfectly inelastic collision? So we're going to let these two stick together after the collision. Like I said, if it's a two-dimensional problem, we're going to have this complication in which we might have to break the information down into x and y components. I've drawn diagrams that I hope will help you visualize the situation. And from those diagrams, I hope you can see that the 16.2 kilogram mass at the bottom makes an angle of 115 degrees with respect to the positive x-axis, which is presumably to the right. And the sphere makes an angle of negative 102 degrees with respect to the positive x-axis. Note that I'm saying negative because going from the positive x-axis directly to the right, if I go in the direction of the velocity for the sphere, I'm moving in a clockwise direction. So I have to go through 90 degrees plus another 12 degrees. That would be 102 degrees, but I went clockwise, so it's negative 102 degrees. Hopefully this makes sense because the next slide is all of our equations. We got to break these velocities into x and y components. So the x component of v1, 4.2 times the cosine of 115, is negative 1.775 meters per second, and the y component is 4.20 times the sine of 115, and that's 3.806 meters per second. For the other mass, the one that is moving 12 degrees west of south, the initial velocity, the x component, is 9.5 times the cosine of negative 102, that's negative 1.975, and the y component is 9.5 times the sine of negative 102, and that's negative 9.292 meters per second. Now that we have their velocities, we can apply the law of conservation of momentum to x. We can apply the law of conservation of momentum to y. If I do it just for x, m1 v1 initial x plus m2 v2 initial x is equal to 16.2 times negative 1.775 plus 11.5 times negative 1.975. And that's equal to negative 51.4675. These two masses stick together afterwards. And so I can determine the final velocity, the x component of the final velocity, because it's going to be equal to m1 plus m2 times the final x. I know m1 and I know m2, 16.2 plus 11.5. So that's 27.7 times the final x. I do negative 51.4675 divided by 27.7. I get the final x equals negative 1.86 meters per second. We do the same analysis but with the y components. And it can be shown that the y component of the final velocity is negative 1.63 meters per second. You should ask yourself, do these values make sense? X component, negative 1.86 meters per second to the left, and negative 1.63 meters per second down when these two objects stick together. If we go back to the picture, we see that both of them have a horizontal component that's to the left. And so I expect that when these two stick together, it's going to remain having a horizontal component to the left. On the other hand, one vertical component is directed down and the other vertical component is directed up. While the velocity of the sphere is greater in magnitude than the velocity of the cube, the mass of the cube is greater in magnitude than the mass of the sphere. So these momenta aren't necessarily exactly equal, but neither are they exactly different in magnitude. They're pretty close to each other. So while I don't necessarily expect complete cancellation in the vertical component, I would expect that after the collision, the vertical component of the combined mass is not going to be large. And that's what we see. We see the leftwards component for the horizontal motion, and we do see a non-zero downwards component, but the speed of 1.63 meters per second is notably smaller than the speeds of the original particles, one of them with a speed of 4.2 meters per second, and the other with a speed of 9.5 meters per second. So this is not an extremely unexpected result. For the magnitude and the direction, we take the x and the y components, we square them, we add them together, we take the square root, and I find that the magnitude of the velocity, the speed, if you will, is 2.47 meters per second. The direction, we do the inverse tangent of y component divided by x component. Since the x component is negative, we have to add 180 degrees to our calculator. This winds up being 221.2 degrees. Moving on, and the final general topic for this pre-lecture is the idea behind center of mass. When I say center of mass, that probably conjures up some sort of concept within you, but I want to make sure that we understand how to calculate it. And when we talk about calculating the center of mass, we talk about finding a weighted average. The average is weighted by the mass of the different objects making up the system. And it depends on how many objects you have. If you have two objects, then the x component of the center of mass is equal to m1 times the x component of the first object plus m2 times the x component of the second object. And then you take that sum and you divide by the sum of just the masses. And as you have additional particles, you just add corresponding terms in both the numerator and the denominator. The y component of the center of mass is calculated exactly the same way as the weighted average, but of course, you use the y components for the locations of the individual masses. The idea of the location of the center of mass, we can also expand on it to look at the velocity of the center of mass. And we can look at it in one dimension, we can look at it in two dimensions, but the velocity of the center of mass goes as m1 times the velocity of object 1 plus m2 times the velocity of object 2 plus m3 times the velocity of object 3, etc., over m1 plus m2 plus m3. And it turns out, and this is not a shock, we've said this before, this is also the idea behind the momentum of a system. M1 times little v1 plus m2 times little v2 plus m3 times little v3 plus yada, yada, yada is equal to the overall momentum of the system. But what it also means is that the overall momentum of the system is equal to the overall mass, m1 plus m2 plus m3, times the velocity of the center of mass. I hope that this intuitively makes sense. It's one of those things where if this weren't true, then reality would be immensely different from what we see. But the sum of the individual momenta equals the momentum of the system. Similarly, I can say the momentum of the system is equal to the total mass times the velocity of the center of mass. Let's take a look at an example, and then we'll call it quits. We have three particles. One has a mass of 10.5 kilograms. It is 5.7 meters away from the origin at an angle of 75 degrees. The second is 12.7 kilograms, 7.11 meters away at an angle of 143 degrees. The final mass is 7.61 kilograms. It's 10.2 meters away at an angle of 299 degrees. All angles measured with respect to the positive x-axis. Okay, we weren't given the x and the y components. What sort of stupid instructor doesn't give you the x and the y components? We got to calculate them. You know how to do this by now, I hope. Magnitude times the cosine gives you the x component. Magnitude times sine gives you the y component. And we do this for each of the three particles. And now we have x1, x2, and x3, and y1, y2, and y3. Let's find the centers of mass, the center of mass, both components of it. The x component, m1 times x1, 10.5 times 1.475, plus m2, 12.7 times x2, negative 5.678, plus m3, which is 7.61 kilograms, times x3, which is 4.945. Don't forget to divide by the sum of just the masses, 10.5 plus 12.7 plus 7.61. And I hope I did this correctly. I got an x component for the center of mass of negative 0.616 meters. The calculation for the y component of the center of mass is done exactly the same way. We use the same m's, but now we use y1, y2, and y3. And if you do that, I hope that you confirm that the answer is 1.44 meters. So that's enough for now. Bye-bye.